We will be looking at the curvature because what you just saw was a curved surface. In both cases, these were curved surfaces. And we will be looking at thermodynamics of pores and Young-Laplace and Kelvin relationship, which explains these things. Okay. So in the last lectures, we were mostly looking at, what we were looking at was 2D plane surface, okay, a plane surface. Okay, this is what we were looking at. But now we are looking at curved surface. ठीक है, अभी हम क्या देख रहे हैं? We are looking at curved surface, curvature. So when curvature comes into play, then the things become a bit different. This is something that you just saw. तो उसमें different considerations होंगी. We will have a discussion about that. So in the last lecture, we defined that the surface tension is the work per unit area needed to create a surface. And we learned that the free energy change, differential free energy change, is surface tension times differential change in area at constant temperature, pressure, and number of moles. And we also observed that this is a very normal condition in which we have constant temperature, pressure, and number of moles. So today we were looking at that what happens when that surface is curved, and you just saw a few demonstrations in which the surface was curved, both in the case of balloon and also in the case of um, soap bubbles, which were connected to each other through a certain arrangement. So the key learning objectives that we have is to know about the Young-Laplace equation derivation, understanding the mechanical consequences of curvature, which is capillarity, and then to link the curvature to phase equilibria, which will be Kelvin equation. So in the absence of gravity, a liquid mass takes a spherical shape. Okay. But obviously, you just saw that the soap bubbles in the demonstration was under the influence of gravity, so it was not perfectly spherical. So this is happening when there is absence of gravity, then the liquid will make a spherical shape. Thermodynamically, for a given volume, a sphere has the minimum surface area, since the surface free energy Gibbs surface energy equals to gamma into area. A sphere represents the minimum energy state. ठीक है, यहाँ पे ये Gibbs energy है, Gibbs surface energy है, so this will be a state energy. So because the surface tension tries to contract the area, it exerts a compressive force on the interior liquid. This results in higher pressure inside the drop than the outside. So what you already know is, let's say that you have a kind of curved surface. So these are two types of surfaces. तो usually हम देखते हैं कि molecules are like this. तो ये fill हुआ. अब यहाँ पर हम देख रहे हैं कि molecules are filling a curved surface. तो यहाँ पर आपके पास जो पुल है वो इस तरीके से नीचे की तरफ है. ठीक है, so we are looking at the inward pull. ठीक है, so when it happens, तो ये क्या होगा, अगर ये if it is pulled inside, then that will be showing a compressive force. जो force होगी वो क्या होगी, अंदर की तरफ होगी, तो वो क्या हो रहा होगा, compress हो रहा होगा. इसमें क्या होता है कि the surface area become minimum when a sphere is formed. So if you have a spherical body formed, then that will give you the minimum surface area. And it means that if the surface area is minimized, then the whatever body it is going to save some एनर्जी। ठीक है, ये बात समझ आ रही है ना आपको? अंडरस्टैंड दैट?
जी सर।
ठीक है, वी आर मूविंग फ्रॉम अ कर्व्ड सरफेस, सॉरी, फ्रॉम अ प्लेन सरफेस टू अ
करेक्ट
कर्व
सर।
सरफेस। ठीक है, तो प्लेन सरफेस में तो इस तरीके से फोर्स थी, यहाँ पर अब जो फोर्स है इट इज इनसाइड लाइक दिस। इसमें भी इनसाइड ही होती है, लेकिन ये क्या है, यहाँ पे आपके पास ये कंप्रेस हो जाता है सरफेस एरिया, बिकॉज इट इज अ कर्व सरफेस, सो दैट्स व्हाई अ स्फीयर इज फॉर्म। ठीक है, सो नाउ here we have a circle, and we just saw that this is the type of force which is happening. So what you see is that inside the circle it is concave surface, ठीक है, and outside the circle it is a convex surface. So the force here that we have is the contractile force which is given by this surface tension. ठीक हो गया? अंदर अब तो नजर आ रहा है ना आपको? अगर इस तरीके की सरफेस होगी, अगर इसमें से कोई पोर्शन हम कट कर लें यहाँ पे, तो कोई भी अगर आप देखेंगे जगह इसमें, फॉर एग्जांपल इस पोर्शन को कट कर लें, तो ये जो पोर्शन है ये क्या है? अगर इसको ऐसे बना दें उल्टा करके, तो फिर तो साफ नज़र आ रहा है ना कि ये आपके पास क्या होगा, कनकेव होगा, और यहाँ से क्या होगा, बाहर से कन्वेक्स होगा। ठीक है, so what we see is that the pressure is always greater on the concave side of an interface। इस जगह पे क्या होगा, प्रेशर ज़्यादा होगा, और बाहर जो है वो क्या होगा, प्रेशर थोड़ा कम होगा। And where is that coming from? From the contractile force exerted by surface tension. और surface tension क्या है? We already know that surface tension is the surface free energy. Now consider a spherical drop of radius r being expanded by dr. पहले उसका रेडियस r था, अब थोड़ा सा एक्सपेंड हो गया, कितना हो गया, dr हो गया। Two energy changes occur. One is that the area is 4 pi r square, and then it is expanded by dA, so 8 pi r dr आ जाएगा, and the work which was used to expand it is gamma dA, which is gamma into pi 8 pi dr। ठीक है, उसको मल्टीप्लाई कर देंगे तो ये आ जाएगा। So work done by the internal pressure will be, in case of volume, 4 by 3 pi r cube, क्योंकि internal pressure तो volume से आएगा ना, so that will be differential of volume 4 pi r square into dr, and dw pressure is equal to delta p dv, which is equal to delta p into this dv। ठीक है, ये समझ गए ना ये बात आप? यहाँ पे ये इसका क्या हो गया, ये डिफरेंशियल आ गया ना, और यहाँ पर भी ये डेल्टा पी को इसके डिफरेंशियल के साथ मल्टीप्लाई कर दिया, तो आपके पास वर्क ड्यू टू इंटरनल प्रेशर आ गया। एट इक्विलिब्रियम दीज टू वर्क टर्म्स मस्ट बी इक्वल, तो आपके पास जो सरफेस वर्क होगा दैट विल बी इक्वल टू वर्क ड्यू टू प्रेशर। जो भी आपके पास प्रेशर होगा, दीज टू विल बी इक्वल। तो ये आपके पास क्या है, एक डी डब्ल्यू प्रेशर है, एक डी डब्ल्यू सरफेस है। सो इफ वी इक्वेट दीज टर्म्स, सिंस अब इक्वेट कब कर रहे हैं, ये यहाँ से याद रखें, इट इज एट इक्विलिब्रियम व्हेन इट इज इक्वल। व्हेन वी इक्वेट दीज टर्म्स वी गेट gamma 8 pi r dr equals delta p 4 pi r square dr, and if we divide both sides by 4 pi r dr we get 2 gamma delta p dot r, and the Young-Laplace equation for a sphere is delta p equals 2 gamma over r। So a liquid drop in air has only one surface, while a soap bubble in air has two surfaces. ठीक है ना, ये आप बात समझ रहे हैं ना। लिक्विड जो ड्रॉप होता है वो क्या होता है, वो तो फुल एक वॉल्यूम होता है ना। यहाँ पर तो इसमें इन अ सोप बबल एयर इज इनक्लोज्ड इनसाइड, सो इट हैज two surfaces, one is inside, one is outside. Using the derivation logic, we just saw what is the equation for the pressure difference across a soap bubble of radius r. So what if the surface is not a sphere? That is, for example, it is an ellipsoidal drop, and at any point on the surface has two principal radii of curvature, r1 and r2. Ellipsoidal drop is just like you saw in the case of soap bubble, and you saw that it was not perfectly sphere. It was rather uh, pulled by the gravity, so it didn't look like a sphere. ऐसा ही था ना? So let's say we have that kind of situation, then we have delta P equals to gamma 1 over R1 plus 1 over R2. Geometrically, if we have a cylinder jet, R1 is equal to R1 into R2, which equals to infinity, and therefore delta P will be equal to gamma over R. If we have a flat sheet, then R1 is equal to R2 is equal to infinity, and therefore delta P is equal to 0 in case of flat sheet. If we have a saddled surface, then R1 and R2 have opposite sign. It is possible for delta P to be 0 even if it is highly curved. That is, if you have a saddled surface. Two soap bubbles, that is, if we have A and B, are connected by a tube with a valve, just that we saw, in which, let's say, RA is greater than RB. ये भी हमने देखा था ना स्टार्ट में कि we have two soap bubbles and they are connected by a tube and one is bigger than the other. ठीक है? So one is smaller and the other is bigger. Then the wall, if the wall is open, then air flows from the large to small until they are equal. Air flows from the small to large until the small one vanishes. So we already know that what happened was क्या ठीक है ना, air flows from the small to large, that is the B1, until the small one vanishes. So the logic is that 4P equals 4 gamma divided by R, that is the smaller R means higher pressure, and air flows from high to low because the pressure will be high in the uh, smaller sphere. ठीक है? So we see that the small bubble empties into the larger one. Now calculate the Laplace pressure inside a water droplet of radius 2 microns at 25 degree Celsius. ये ज़रा कैलकुलेट करके देखें डेल्टा पी क्या आएगा उसमें। इसको अगर आप ऊपर देख लें, ये लिख लिया आपने अपने पास प्रॉब्लम? जल्दी से बताएं मुझे, मैं फिर
जी
आपको
सर।
इक्वेशन ऊपर ले जाऊँ इसको। ठीक है, कहाँ रोकूं इसको? ठीक है, तो यूज दिस इक्वेशन टू कैलकुलेट व्हाट वी जस्ट सॉ। ठीक है ना?
जी सर। ठीक है।
मैं आगे जा रहा हूँ उसमें वापस प्रॉब्लम के पास।
सर 72 किलो न्यूटन पर मीटर।
72 किलो न्यूटन पर मीटर है। अभी गर्ल्स, आप लोगों ने कैलकुलेट किया, कैसे ही बैठे हुए हैं? दोबारा देखें क्या आएगा, यही आएगा।
सर अगर यूनिट्स चेंज करें तो सर यही आएगा।
What it shows is that there is a massive pressure for this small droplet, and this is the driving force behind Ostwald ripening, where small particles dissolve more easily to feed larger ones. ठीक है, अब अगर आप उस demonstration को, if you remember that, then the smaller bubbles were feeding the larger bubbles, and the smaller bubbles were collapsing to form a larger bubble. ऐसे ही हो रहा था ना? And this is because they have a very high pressure. ठीक है, उसका प्रेशर काफ़ी ज़्यादा होता है, जिसकी वजह से that happens. The same is true for nanoparticles. So if there are very small nanoparticles, they will be highly energetic, especially because they have this curved surface, and the curved surface is again bound to form. अब ये आपको formation of uh, spherical bodies के रह गए भी। पहले तो ये हो रहा है कि फॉर्मेशन ऑफ स्फेरिकल बॉडीज, वाई स्फेरिकल बॉडीज आर फॉर्म, ऐसा क्यों हो रहा है? ये हमने डिस्कस किया ना, कैसे वाई स्फेरिकल बॉडीज आर फॉर्म। तो दिस इज द फर्स्ट थिंग दैट हैपन, दैट पहले तो आपके पास यू हैव दिस फॉर्मेशन ऑफ स्फेरिकल बॉडीज। ठीक है, उसके बाद जब वो हो गया and they are small, then the small ones have very high internal pressure and they are again not stable. So they are dissolving to feed the larger ones and they are still unstable. ठीक है, इनिशियली हमने क्या देखा कि आपके पास अगर कोई आपके पास लिक्विड है, तो it has to go into a spherical shape. But those spheres which are formed, if they are small in size, they are highly energetic and they feed the larger ones. ठीक है, you understand that? So
जी सर।
when a small tube is dipped in liquid, the meniscus is curved. This creates a pressure difference across the surface. Small tube mean if a capillary is dipped in liquid, so the meniscus is curved. So that will create a pressure difference across the surface. So if we have water glass interface, the concave meniscus is obtained, which means that pressure below is lower than the atmospheric pressure and the liquid is sucked up. If it is non-wetting situation, that is the mercury and glass, then the convex meniscus is formed, pressure below is higher than the atmosphere, liquid is pushed down. Okay, these two types of situation can happen. At equilibrium, the upward force of surface tension balances the weight of the liquid column. The upward vertical force will be equal to this surface tension multiplied by the perimeter multiplied by cos theta equals gamma into 2 pi r, which is the perimeter, into cos theta. The downward gravitational force will be given by mass into g equals to pi r square h into rho into g. तो ये तो आपको पता है, this will be for water, this will be for the mercury. क्योंकि water will be sucked up and mercury will be coming down. So if we have this upward force equal to downward force, then we can take the equality of these two equations and get this equation. And from there, we get the Jurin's equation, which says that the height of the column will be equal to 2 into surface tension into cos theta divided by r into rho into g. This is also an important equation and used to calculate the height of a liquid in a capillary or in a tube. Now, the Laplace pressure does not just affect mechanics, it affects the chemical potential. Increasing pressure inside a drop increases the tendency of molecule to escape. The result is that the small droplets have a higher vapor pressure than a flat surface. So let's say if we have this Kelvin equation, log of P over P naught, 2 into gamma into Vm. तो ये तो आपके पास आपको पता है surface tension हो जाएगा, this will be molar volume, and then this is R subscript G into T dot R. तो ये मेरा ख्याल है रेडियस ऑफ जायरेशन, और ये आपके पास केल्विन टेम्परेचर, और ये रेडियस हो जाएगा खुद ना. So consider the sign of the radius r. If we have convex surface, that is, if we have a droplet, then r is positive. P will be greater than P naught. Small droplets evaporate faster than the larger ones. If we have concave surface, that is, if we have a pore or capillary, then R is negative. P will be smaller than P naught. Vapor pressure is lowered inside a pore. This leads to capillary condensation. Liquid can condense in small pore even if the air is not saturated. P will be smaller than P naught. Most industrial catalysts rely on massive surface area provided by pores. According to Kelvin, the chemical potential in these small pore is different. If you heat the system, the small particles evaporate or diffuse through the surface to join larger ones. And this is very particular of nanoparticles. So even they can auto-sinter. If they are very small in size, they will auto-sinter. So this destroys the surface area and kills the catalyst activity. The Kelvin equation is the villain of catalyst lifetime. Curvature creates a pressure difference, which is delta P, given by delta P, you just calculated that, and which equals to 2 gamma over R, given by Young-Laplace equation. Smaller radii result in significantly higher internal pressures. Capillary rise is the balance between this Laplace pressure and gravity. The Kelvin equation proves that smaller particles are more volatile and pores can trap liquid via reduced vapor pressure, which can actually naturally happen. In a polydisperse emulsion, that is when the droplet sizes are mixed, the smaller droplets vanishes while the larger ones grow. So obviously if this happens, it again leads to overall instability of the emulsion. So it means that somehow this has to be decreased, the polydispersity. Instead, it should be taken to smaller particle size and avoiding of mixed sizes. So why this happened? Because of the Laplace pressure and Kelvin equation. Again, the trick is that even if the smaller droplets are formed, how they are going to be kept as such, that is in the smaller size and stable. So if you want to stop this, should you make the emulsion monodisperse, all same size, or polydisperse? Obviously, what would be the answer to that? क्या monodisperse small size होंगे तो फिर ऐसा नहीं होगा कि एक दूसरे को फीड कर रहा हो, क्योंकि वो सारे एक तरह के होंगे। ठीक है, लार्जर में फिर भी प्रॉब्लम है, क्योंकि लार्जर खुद अनस्टेबल होंगे। लार्जर जो आपके पास साइजेस होंगे उस पर ग्रेविटी इफेक्ट ज़्यादा होगा, तो फिर वो आपके पास वैसे ही अनस्टेबिलिटी होगी। और अगर लार्जर और स्मॉलर होंगे तो स्मॉलर अनस्टेबल हो जाएंगे एज कम्पेयर टू लार्जर ones. They will continue to feed the larger ones, and therefore it will become unstable. So if you have monodisperse and smaller sizes, then there is more chance that it will be stable, provided that the other stability factors are also handled. ठीक है। So next time we will be looking at the noise ring method, and that is how we can measure the basically this method is used to measure the surface tension. With me plate again, it is used to measure surface tension and contact angles. And then pendant drop method is also used to understand the drop shape analysis and also for measuring surface tension. That. So if you again, we already know that we have bulk molecules, and bulk molecules are surrounded by identical neighbors. Attractive cohesive forces are balanced in all direction, and the net force is equal to 0. आपको ये बिल्कुल सबको पता है. Then we have surface molecules. Neighbors are missing on the outside. This creates an net inward attraction normal to the bulk. And then we have a resultant lateral tension. This inward pull draws surface molecule closer together, stretching the lateral intermolecular springs beyond their equilibrium length. तो आपके पास क्या हो जाएगा कि if we have that kind of situation, तो हमारे पास kind of skin is formed. ठीक है, बिल्कुल उसके टॉप पे एक स्किन की तरह का स्ट्रक्चर बन जाएगा in case of these type of materials. ये बात समझ रहे हैं ना कि क्या हो रहा है यहाँ पे, कि आपके पास अगर आप सोचें तो इफ़ यू हैव समथिंग लाइक दिस, ऐसे है आपके पास एक चीज़, और पहले तो हम जब वो टेबल क्लॉथ की बात करते हैं तो वी आर टॉकिंग अबाउट समथिंग समवन, अगर यहाँ से यहाँ तक वो टेबल है आपका, तो समवन इज पुटिंग हेयर। लेकिन आप ये सोचें कि इफ़ दे आर मॉलिक्यूल्स, सो बेसिकली इट्स नॉट लाइक, आपके पास क्या होता है कि हर पॉइंट के ऊपर इट इज पुल डाउनवर्ड, ऐसे ही है ना। इसका मतलब है कि जो फोर्स यहाँ बनेगी इस जगह पे, जो डाउनवर्ड पुल होगा, तो इस वजह से हर पॉइंट के ऊपर आपके पास स्ट्रेच होगा इस जगह पे। ठीक है, हर पॉइंट के ऊपर आपके पास स्ट्रेच यहाँ पे बढ़ता जाएगा। यू कैन इमेजिन दैट surface tension is a lot stronger in that kind of situation. समझ गए ये बात? So imagine a child pulling down the center of tablecloth. Even though the force is vertical, it creates a horizontal tension that supports item on the surface. Every molecule at the surface represents a broken or unsatisfied bond. Creating an interface increases the Gibbs free energy of the system. Gxs equals gamma into A. To reach the lowest possible energy state, the liquid must conform to the shape that encloses its volume within the minimum possible surface area. So a sphere is the unique shape that provides the minimum surface area for a given volume. ठीक है, ये हम बार बार कहते हैं कि दो चीज़ें इसमें देख लें कि एक आपके पास क्या है कि इट इज़ प्रोवाइडिंग मिनिमम सरफेस फॉर अ गिवन वॉल्यूम। दो चीज़ें हैं इसमें, मिनिमम सरफेस फॉर अ गिवन वॉल्यूम। इफ़ देयर इज़ सम अदर शेप फॉर द सेम टाइप ऑफ सिचुएशन, देन द सरफेस एरिया विल बी डिफरेंट। ठीक है, और मिनिमम नहीं होगा, ऑब्वियसली इट विल बी मोर देन दिस वन सरफेस एरिया. सो देयर इज अ डिफरेंस ऑफ एनर्जेटिक्स. सरफेस एरिया अगर बढ़ता है तो एनर्जी क्या होती है? इफ सरफेस एरिया इज इंक्रीज्ड, व्हाट हैपेंस टू द एनर्जी? ठीक है, तो यहाँ पर हम कहते हैं कि a sphere is the unique shape that provide the minimum surface area for a given volume. तो इसका मतलब है कि if something is acquiring spherical shape, it will get minimum surface area, hence energy will be saved. ऐसे ही होगा ना, एनर्जी लो होगी उसकी. बात समझ रहे हैं आप लोग? अगर
जी
कोई
सर।
और शेप होगी ना, कोई क्यूब बनेगा या ऐसी कोई चीज बनेगी, तो एनर्जी क्या होगी? ज्यादा होगी.
जी सर।
एनर्जी बढ़ जाएगी, द सिस्टम विल बिकम अनस्टेबल.
इंस्टेबल।
ठीक है.
जी
तो
सर।
इसका इसका ये मतलब नहीं है कि स्फेरिकल पार्टिकल बहुत छोटे साइज के होंगे तो वो स्टेबल हो जाएंगे. लेकिन अगर वो सेम चीज क्यूब की होती तो क्यूब ज्यादा अनस्टेबल होता. ठीक है. So let's say we compare a sphere and a cube of the same volume, that is 1 meter cube. So for a cube, we have B is equal to S cube is equal to 1, S is equal to 1. So area is 6S square or 6 meter square. In case of sphere, we have 4 pi r cube is equal to 1. ठीक है, R1 हो गया तो आपके पास R 0.62 मीटर, तो एरिया आ जाएगा, एरिया विल बी 4.84 मीटर स्क्वायर. तो यहाँ पे आप देख रहे हैं that there is a big difference between the two areas. The area of sphere for the same volume is smaller. ठीक है. So thermodynamically, for a liquid like water, for which gamma is equal to 72 millijoule per meter square, forming a cube cost 432 millijoule of work, while a sphere costs only 348 millijoule of work. So in this way, we see that the system saves energy by being spherical as compared to any other shape, because it has been saving energy for the same volume. So if we look at the Young-Laplace pressure that we just saw in the lecture, then delta P is equal to 2 gamma or R, compress the liquid inside a drop, increasing the chemical potential of its molecule. So basically, we have log of P over P set equal to 2 gamma Vm. P saturated, ठीक है ना, saturation pressure है ये, and RTR. So this is the vapor pressure over a curved surface, vapor pressure over a flat surface. We see that the molecule in a tiny droplet are high pressure. They want to escape back to vapor phase more than molecule in a flat surface. Consequently, small droplets have higher vapor pressure than bulk liquids. If tiny droplets evaporate more easily, how do they ever grow into rain? फिर होता क्या है जब if they are evaporating easily, then how would rain happen? So the barrier to form a droplet from vapor, you must pass through a stage where R is nanoscopic. That is, let's say R is equal to 1 nanometer, the vapor pressure is 3 times higher than the saturation pressure. This creates an energy barrier for homogeneous nucleation. ठीक है. So dust particles or ions provide a ready-made surface with large radius. तो उसको क्या करेगा, ये इसको फीड करेगा ना. सो बाय स्टार्टिंग ऑन द न्यूक्लिएशन साइड, द एम्ब्रियो bypasses the high pressure region of the Kelvin curve, allowing the rain to fall even at low supersaturation. In a polydispersed system, that is mixed sizes, material is transferred from small to large particle. This is something that we saw, and we also saw the demonstration. Small droplets have high vapor pressure. They evaporate, that is dissolve faster into the medium. Large droplets, lower vapor pressure, act as sinks and collect this material. So Do you have any questions?